Chapter 9 is on inferences from two samples. So this is a continuation of what we saw in Chapter 8, but now from dealing with one mean, one proportion, we're going to extend this to two means and two proportions. So section 9.1 is on two proportions. And it says in section 7.1 and 8.2, we discuss inferences regarding a single population parameter proportion. The concept used in these previous sections will be extended to include two samples now. So a hypothesis test, again, is to conduct a hypothesis test of a claim about two population proportions. And we're going to be using confidence intervals also. So to construct a confidence interval estimate of the differences between the two population proportions. So we also have a few review words here. We do have independent and dependent sampling methods. So independent is going to be when individuals are selected for one sample and they do not dictate which individuals are going to be in that second sample. And technically, adults and children and people are going to be independent of one another. The only time that they're going to be dependent sampling is going to be if we were matching you up maybe with a sibling, with a parent, with a spouse, something that's going to dictate who gets selected in that second group based upon you and your characteristics. So a dependent sampling method or match pair sampling is when individuals are selected to be in one sample are used to determine the individuals in the second sample. And also note that individuals can be matched up against themselves. So maybe like a pre-test, post-test, or seeing like left hand response to right hand response for different things. And then some more words here that we've seen previously, but just to kind of review. We have qualitative and quantitative data. So these are going to be data that cannot be expressed as a number, and that is qualitative. Whereas quantitative is going to be data that are anything that can be expressed as a number. A response or dependent variable is a particular quantity that we are asked a question about in our study. Next up, it says sampling distributions of differences between two proportions. And this is going to be dealing with independent samples. And so it says, suppose a simple random sample of size N1 is taken from a population where X1 of the individuals have a certain characteristic. And then likewise for a second sample, we'll say of size N2 with that same characteristic, but X2 has that characteristic. So the sampling distribution of P1 hat minus P2 hat, where P1 hat is X1 over N1 and P2 hat is going to be X2 over N2. Is approximately normal with a mean, and you'll notice that difference in there, and a standard deviation that's given by the square root of p times 1 minus p divided by n for each of those two cases, but added together and then taking the square root of it, provided that n times p and n times q are both greater than or equal to 5 for both samples, and each sample size is no more than 5% of the population size. The standardized version of P1 hat minus P2 hat is then written as, and you'll notice that we are using a z-test statistic here, which again is given by the same thing that we have seen before, which is going to be x minus x bar divided by our standard deviation, which has a approximate standard normal distribution. Says the null hypothesis is a statement of no difference and is always going to be H naught is going to be P1 is equal to P2 because H naught is assumed to be true. This implies that if you were to subtract them, if they were equal, that means that they would be equal to 0. And we also assume that P1 minus P2 is equal to P. So that's going to be our population proportion that we're dealing with. The example at the bottom of the page says determine whether the sampling is dependent or independent and indicate whether the response variable is going to be qualitative or quantitative. So part A says a researcher wishes to determine the effects of alcohol on a person's reaction time to a stimulus. She randomly divides 100 people aged 21 years of age and older into two groups. Group 1 is asked to drink 3 ounces of alcohol, while group 2 is asked to drink a placebo. Both drinks taste the same, and the individuals in the study do not know which group they belong to. 30 minutes after consuming the drink, the subjects in each group perform a series of tests meant to measure reaction time. So the first thing is that these people have nothing to do with one another, and they're independent of one another. And we are asked to measure reaction time. So this is numerical, so this is going to be quantitative. Part B says a political scientist wants to know how a random sample of twins over 18 years of age feel about Democrats in Congress. She obtains a random sample of 224 registered voters who are also twins and asks, do you have a favorable/unfavorable, and she rotates that wording, opinion about the Democratic Party. Each individual was asked to disclose his or her opinion about the party, and the twins' opinions were recorded. So since we are dealing with twins, if I select one person, I must select their twin to compare them to. So we're going to look at dependent sampling here. And this is asking about his or her opinion, so that's not numerical. And so this is going to be qualitative. At the top of the next page is our directions on how to use our graphing calculator for the TI-83 or 84. So a hypothesis test regarding the differences between two population proportions with a graphing calculator. The first thing that we need to do is check the requirements, and those requirements that we have to verify are listed here. First one is going to be that both samples are random. The second one is that the two samples are independent, and then we also have n times p and n times q are both greater than or equal to 5 for both samples. The next step is to determine the null and the alternative hypotheses. H0, our null hypothesis, is the same for all three cases, and H1, our alternative hypothesis, is going to depend on if it's a two-tailed, left-tailed, or right-tailed test. So make sure that you carefully read the problem to find the words that tell you which type of testing that we're using. Step 2 is our level of significance, which is alpha, which is usually given to us. Step 3, you go to stat button, test to prop z test. And over here, I do have a list of what the screenshot will look like for the more recent calculator. Again, if you're using a different calculator or app, make sure to edit the notes to fit your specific application or calculator that you have. So next thing is you're going to enter in the values for x1, n1, x2, n2. Select the appropriate relationship between p1 and p2. That would be alternative hypothesis. And then calculate. From there, we're going to get two outcomes that are important to us. One's going to be z, which is our test statistic, and p, which is our p-value. You'll notice that this is the same as what we've seen in the previous chapter. If the p-value is less than alpha, we reject our null hypothesis and then stating our conclusion as we've done before. So right below this, it does say, we can also consider a confidence interval estimate of the differences between population proportions P1 minus P2. If the confidence interval estimate of P1 minus P2 does not include 0, and again, remember our null is saying that they are equal, so if you subtract them, you should get 0. We have evidence suggesting that P1 and P2 have different values. Consequently, a conclusion based on confidence intervals might be different than a conclusion with hypothesis testing. So confidence intervals are always needing to be set up as a two-tailed test. So this is really important to remember, is that we do always need to set them up as a two-tailed test. So kind of forcing that problem, if it is a left-tailed or right-tailed, to be a two-tailed test. And we'll go through different scenarios in the notes. So you'll see all three cases set up as you work through the notes. So to conduct a test using the confidence intervals and finding a confidence interval, and then you're going to check to see if 0 is in the interval. And so if 0 is in the confidence interval, then we do not reject the null hypothesis. And if 0 is not in the confidence interval, then we reject the null hypothesis. So right below this are steps for constructing a confidence interval for the difference between two population proportions, again, independent samples, with our graphing calculator. First thing is checking those requirements, and they should look familiar. They should be the same as what we just saw up above. And step 1 is going to go to stats, test to prop z int this time, and you're going to enter in x1, n1, x2, n2, enter your confidence level, and your calculator is going to give a lower bound and an upper bound, and then you need to interpret your results. And this is the same thing that we had up above in checking to see if 0 is in the confidence interval or if it's not in the interval. So on the next page, we have an example, and the example says to test whether P1 is less than P2 at the alpha equals 0.05 level of significance. We have sample data with x1, n1, x2, and n2, and it says assume that the sample is obtained independently using simple random sampling. Part A says determine the null and alternative hypotheses. So H naught and H1. Well, we were given up above that P1 is less than P2. Our null is going to be identical to this, except for instead of that inequality, it would have an equal sign. So P1 is equal to P2. Part B says determine the test statistic. So using our test statistic, we need to go to 2 prop Z test. On the graphing calculator, we're going to go to stat, to test, and then down to 2 prop Z test. On here, you need to make sure you select x1, n1, x2, n2 values that are given to you in the problem. Make sure those are correctly typed in. Make sure that you have a left-tailed test selected also, since that's our alternative hypothesis. And you'll notice that our z-score is given, which is our test statistic, and our p-value is given. We're going to round our z-score correctly 2 decimal places and our p-value correctly 4. From the graphing calculator, we get a test statistic of z equals negative 0.35. And again, this is our test statistic. Determine the p-value and conduct the test. So as we saw, we had a p-value. And then again, this is going from 2 prop z test. Our p-value, again, running 4 decimal places, is going to be 0.3649, which is greater than alpha, which was given to us as 0.05. And so this means that since our p-value is greater than alpha, we do not reject H naught. And so our conclusion would be there is not sufficient evidence to support, and again, this isn't too much of a word problem, it's more or less going through those mechanics with the graphing calculator to support the claim that P1 is less than P2. And again, when you have more of a word problem, make sure you explain it in words. The second part on here is making a confidence interval instead of using that p-value method. And we're testing the same hypothesis that was given in part A. And so for this, we're going to go ahead and draw a normal curve. And since we are dealing with a left-tailed test, again, because that less than symbol, that means that over here my left tail will be my alpha. And my alpha value is equal to 0.05. But as stated earlier, in order to do confidence intervals, we do need to have a two-tailed test. So because of symmetry, I'm going to force this to also have another tail. It would be the same exact size. This is also going to be 0.05. And remember that total area under the curve is equal to 1. So if you were to do 1 minus 0.05 minus the other tail, which is 0.05, we're going to get a confidence level of 0.90. And so that's what's called our C level. On the graphing calculator, we're going to go to stat, test, and then down to 2 prop z int for our confidence interval. Make sure you enter in x1, n1, x2, and n2. And then also your C level or your confidence level is 90% or 0.90. And then when you do this and you select enter, you are going to get a lower bound given and an upper bound. We're going to round these correctly 3 decimals. From the graphing calculator, we get an interval of negative 0.061, comma 0.040. And so if you notice, one of the values, our lower bound is negative and our upper bound is positive. So that means 0 is in the interval. So 0 is in the interval. And this means we do not reject H naught. So we have another word problem underneath this. And this example says, a study was conducted to determine the proportion of people who dream in black and white instead of in color. Among 306 people over the age of 55, 68 dreamed in black and white, and among 298 people under the age of 25, 13 dreamt in black and white. And this is based on a study that was done. And it says we want to use a 0.1 significance level and to test the claim that the proportions of people over 55 who dream in black and white is greater than the proportions of those under 25. So notice it does say greater than, so we know that we'll probably be dealing with a right-tailed test depending on how we set this up. So make sure that you label your two groups. So I'm going to go ahead and call P1 my group 1, which is going to be over 55 in age. And then P2 is going to be the younger group, which is going to be under 25 in age. So we need to have an X value and an N value for both of those. And so if you read the problem again, carefully looking at those numbers, it does say that for the age of 55, there is a total of 306 people. And it says 68 of them dreamt in black and white. So that's that specific characteristic that they have. Whereas 13 people that were under 25 out of a total of 298. And these are going to be the numbers that we use in our calculator. So next thing we need to do is set up our null and our alternative. And since I already have defined what P1 and P2 are representing, I'm going to go ahead and use those values. Make sure to state this and not just put a 1 and a 2 without defining what they're representing. So our null is going to be that those two proportions are going to be equal to each other. And for our alternative is going to be that proportion 1, which is the people that are over 55, is greater than the proportion 2 or under 25. On your graphing calculator, we're going to go to Stat, to Test, and then we're going to go down to 2 Prop Z Test. Select this. You need to enter in your X1 value and your N1 value. This is for over 55. Your P2 values for X and N, which is going to be under 25 age group. And then also make sure that you select a right-tailed test and select enter. Your p-value, you'll notice, is given, and there should be an e in there. When you round this value that you get, make sure that you convert it to a decimal and you round 4 decimal places. From the graphing calculator, we get a p-value equal to 6.01 times 10 to the negative 11th. So moving that decimal point 11 times to the left, we would have point and then 10 zeros and then 601. Since we do round our p values 4 decimal places, this would just be 0.0000, which is less than alpha, which was given to us as 0.01. And so because of this, we are going to reject H naught. And so writing our conclusion and making sure that our conclusion is written using the words that are in the problem and explaining that, we're going to say there is sufficient evidence at the alpha equals 0.01 level of significance to conclude that the proportion of people over 55 who dream in black and white is greater than those under 25. Part B is testing the claim by constructing a confidence interval for this one. So again, we're going to start by drawing our normal curve. I'm going to look at what I have in my hypotheses, and I notice that this time I have a right tail test because of that greater than symbol. It's a right tail test, so in the right side of my graph, I'm going to go ahead and put my alpha, and this time my alpha is equal to 0.01. But again, remember, in order to test our hypothesis with a confidence interval, it does need to be set up as a two-tail test. And because of symmetry, that means that this side over here is also going to be 0.01. So in order to find that confidence level, which we have right here, our total area under our curve for our normal curve is equal to 1 minus that 0.01 and minus the other 0.01, and we get a C level that's equal to 0. On the graphing calculator, we're going to go to Stat, test and down to 2 prop z int for our confidence interval. And on here, you need to enter in x1, n1, x2, n2, like we did previously. In our confidence level, make sure you select it as 0.98 and then select enter. And from here, we're going to get a lower bound and an upper bound, and we're going to go ahead and round those both 3 decimal places. From the graphing calculator, we get a confidence interval of 0.117, 0.240. And this time 0 is not in the interval. And this means that we would reject our null hypothesis. The next section begins on the next page, and this is section 9.2. So this is going to be 2 means and independent samples. So 9.2 says, in this test, we collect 2 independent samples to test whether there is a difference in means between the 2 populations, or if one population mean is greater or less than the other. Comparing SAT scores between men and women is an example of 2 independent tests sample. And so sampling distributions of difference of 2 means independent samples with population standard deviation unknown, or Welch's T. So suppose that a simple random sample size n1 is taken from a population with unknown mean mu1 and an unknown standard deviation sigma 1. In addition, a sample also for n2, same idea. And it says the 2 populations are normally distributed, or the sample sizes are sufficiently large, meaning that, again, they're greater than 30 for both of them, then we're able to find that test statistic. Again, our calculator is going to help us out with this, and you will not need to do that by hand. Approximately follows a student t distribution with a sample of the smaller n1 minus 1 or n2 minus 1 degrees of freedom, where x1 bar is the sample mean and S2 or S1 is the sample standard deviation of the population for population 1, and likewise for population 2. So right below this, we have steps for how to use our graphing calculator, and this is testing a hypothesis regarding the differences of 2 independent means with the TI-8384 calculator. And so the first thing that we need to do is check our requirements. And the requirements are listed. It says that both are simple random samples. The 2 samples need to be independent, and the differences are normally distributed with no outliers, or the sample size is large enough, meaning that both of those sample groups that we have are going to be greater than 30. The next step is going to be to find our null and alternative hypotheses. The null is the same for all 3 cases, saying that mu1 is equal to mu2. And then your alternative hypothesis depends on if it's a 2-tailed, left-tailed, or right-tailed test. So step 2 says to determine your level of significance, which is alpha, which again is usually stated to us. And then step 3 is you're going to go to stat, test, and we have 2 SAMP T tests. A little different here because you're going to toggle between either data and stats. And I did give images for both of these for the newer version of the calculator. And again, edit this if you have a different app or calculator that you're using. But if the data is raw, you're going to put your data into L1, listing all those numbers, and L2, listing all those numbers. Set frequency is equal to 1. And if summary statistics are known, that means that you would know the mean and the standard deviation and sample size for both sets of data. And then you're going to highlight the appropriate H1 that you have. Set pooled to no. And then you're going to highlight, calculate, or draw and press enter. From here, you're going to get your T, which is your test statistic, and P, which is your p-value. Draw gives the graph. It's something kind of neat to look at. But step 4, the p-value is less than alpha, reject your H0. And then your last step, again, is always to state that conclusion.